So I have 10 minutes before I have to go to another meeting, so I think I'll squeeze in this podcast here. We looked at this figure before in the context of explaining feedbacks in the Earth system, so I'm just going to use it again about how we talk about the basic outgoing infrared long wave radiation. So if you have somehow changed the solar constant and the incoming solar radiation and put more energy into the system, that would then increase the temperature and increase the outgoing long wave radiation, which would be a negative feedback like a thermostat. On the other hand, if the increased radiation goes into melting permafrost, which then increases greenhouse gases in the atmosphere, that can be a feedback in the system as well, because that then affects carbon cycle, saturation of carbon sinks in the ocean circulation changes that we talked about, and you can also be adding another signal from burning fossil fuels, and that would reduce the outgoing long wave radiation because you are trapping more energy into the system, and that would then be going in the other direction to increase the warming. So that would be, so if you reduce this, then you increase the energy retained. So these signs have to be watched out carefully, and we talked about the aerosol feedback as well. So without going into further details, this is another figure we looked at, which is the focus of this particular chapter, looking a lot at how climate changed and how vegetation changed, and in terms of plant species and functional types like C3 and C4, which we have mentioned that C3 is a photosynthetic pathway more energy efficient, but C4 grasses, which use 4 carbon molecules in the photosynthetic pathway, are less efficient, but they compete better in warmer conditions. So you have increasing daytime growing season temperature here, increasing atmospheric CO2. So you can see that colder temperatures and higher CO2 favor C3 grasses. Then they begin to get outcompeted as you go towards warmer temperatures, and CO2 ranges can be anywhere here. This is the mid-Pleistocene transition, and this is after the mid-Pleistocene transition, where we went from one time scale to other. So this is prediction of atmospheric CO2 and daytime growing season temperature conditions that favor C3 or C4 grasses. Black box covers CO2 levels and potential temperatures during glacials in the central interior of South Africa before the mid-Pleistocene transition. So that's the 40,000-year obliquity cycle to mid-Pleistocene transition, where we went into 100,000-year ice age cycles. So looking at one particular example then on these time scales, we are here looking at the dust flux going back to over 80,000, this is the latitude, and we are looking at concentration distribution in a meridional sense in the Holocene mean. This is the Holocene median, where we have more data, of course, now. Estimated from the past, you have last glacial maximum mean, which is about 20,000 years ago, and the median. Obviously, dry glacial periods have much higher dust fluxes on average in grams per meter squared per year. This is a global number. In general, climate is drier, rainfall is reduced, to more dust. And if you look at the mean and median of the ratio of last glacial maximum to the Holocene levels, then you see that signatures are a little bit more distinguished in terms of the peaks, so the mean and the median. So you can see now the latitudinal dependence of the ratios. Okay, so tropics, the changes are not as large as you can imagine, lower latitudes, but as you go to higher latitudes, the differences during the glacial and interglacial periods get larger, which we talked about in terms of dust deposition, iron fertilization, and photosynthesis in the Southern Ocean. But you also have to worry about this in terms of other feedbacks like radiative forcing. How much solar dimming is affected by these latitudinal dependence of the changes. So zonal mean and median dust deposition for the Holocene, last glacial maximum rates and ratios of these rates calculated from this reference data. Blue points in B are the LGM to HOL ratios for the individual dust deposition time series considered in another figure from this paper. Also indicated are the latitudes for the Atlantic EDC, Epicodome core, and NGRIP core from Greenland temperature anomalies. So without going into those details, just remember, so looking at the impacts, here we are looking at Antarctic temperature anomaly signal, and time is here going more than 300,000 years, and this is the scaled southern hemisphere dust flux from various sources. So obviously you have, again, going forward in time, glaciation, deglaciation, glaciation, deglaciation. So you can see the peak of the dust flux in the southern hemisphere and the northern hemisphere are different, and the Greenland delta T and Antarctic delta T are almost in phase, as the glaciation at that scale is global in terms of a temperature signal, which means that vegetation signal, sea level signal, dust loading, impacts of dust, impact of vegetation, and vegetation feedback to CO2 and albedo and energy exchange will also be very regional and local. Okay, so here the time series is shifted to show better matches between the northern hemisphere dust fluxes and Greenland temperature anomalies and so on. So there is a hemispheric asymmetry in the dust loading, the radiation forcing, and we talked about the various connections like the bipolar seesaw and so on. So all these things have to be considered when we do modeling. So this just confirms that dust flux, whether it's in Antarctica or the Southern Ocean or the Chinese Luss-based dust flux and the global mean and global median, are all temperature dependent. So as temperatures cool, dust loading goes up exponentially as you get beyond a certain threshold. So there is a large scatter in the Chinese Luss. Chinese Luss is basically fine dust whose concentration and size fraction, etc., will depend on the amount of rainfall. So they have to be carefully calibrated to relate to rainfall changes, temperature changes, and other changes. But still, you can see this consistent signature. When the dust loading of the Chinese Luss goes up, temperatures are colder in Antarctica and as well. Southern Ocean dust flux is important because that can lead to the iron fertilization and CO2 drawdown, which can help positive feedback in the cooling direction as well as in the warming direction. So globally, again, the temperature dependence is not as strong as you saw locally. So you can see that the global means are here, and these are the various dust fluxes and Greenland temperature anomalies. So these are the same curves that we are looking at here. So the scales are different, so that's why we are put together. They look different. This scale here is up to 30, up to 5, up to 5, and this is up to 1,000 in terms of grams per meter squared per year here. Okay, so just remember that then comparing data with comparison of with data and data-based reconstructions over the last glacial cycle of a model simulation for combined dust, radiative, and iron fertilization forcing. So as we said, dust affects radiation balance, especially top. Anytime we say forcing, we mean radiation perturbations at the top of the atmosphere in terms of incoming solar, outgoing long wave, and how they are balanced, right? So this is a simulation of PCO2 anomaly from 278 ppm, which is the deglacial level, pre-industrial level. So this is the blue line here. PCO2 anomaly from observed Antarctic ice core, which is this black line, and the residual anomaly after subtracting model results from observations, which is a way of making sure model is not going crazy. So you can see the high correlations there, except for some differences. B is the simulated anomaly from a Holocene mean of the global mean temperature and residual anomaly after subtracting model results from a GMT anomaly reconstruction, which is shown in the red line. GMT anomaly reconstruction is based on sea surface temperature reconstruction with a 3 kiloyear resolution. So depending on which proxy you use, the time resolution of the temperature proxy or any other proxy can be very coarse in time. 3000 year is what you get in terms of the average signal. Adjusted for agreement with a comprehensive global mean temperature reconstruction at the last glacial maximum, so it's calibrated against some period that is better constrained. The dotted line is the mean summer incoming radiation at 65 north. As we said repeatedly, 65 north is a critical latitude which can trigger either deglaciation or glaciation. So PCO2 anomaly, as you can expect from the glacial deglacial changes we have seen, and this is the insolation, how it has varied at the various time scales, and the global mean temperature anomaly. So you can see how radiation forcing works, and this is the reconstructed dust forcing time series for the last 3 glacial cycles. I won't go into the details, but radiation forcing in watts per meter squared can be substantial in spikes, and this is the Southern Ocean iron fertilization parameter, which can also be very strong based on how high the dust loading is. One has to be careful here because we don't know how much of the dust is actually iron, and even we know that, then we don't know how much of that falls into the ocean is bioavailable. So there may be iron, but it may not be usable by the phytoplankton. So there are lots of details in the assumptions that go into these, but here we are mostly looking for consistency between glacial, deglacial, temperature changes, dust loading, iron fertilization potential, and CO2 signal. So in that context, this model is being used that we have talked about before. So the University of Victoria Earth System Climate Model has very coarse resolution, 3.6 degree longitude and 1.8 degree latitude, with some vertical resolution in the atmosphere and the ocean, and has various processes like sea ice but not land ice, has a permafrost model, land surface model which does hydrology, vegetation, so it has a vegetation model, and it has fluxes of energy, water, and carbon. Carbon cycle is important. So ocean general circulation model, it does carbon cycle, nitrogen, phosphorus, oxygen, organic carbon cycle, inorganic carbon cycle, marine sediment model, and so on and so forth. So this is what the model that is used in great detail to discuss the results for each marine isotope stage that we will look at along with the vegetation changes. Okay, I'll come back to that.